Good morning, everybody. So I'm going to presentation mode. I'm Maria Federica Marcucci. I'm a senior research scientist at the National Institute for Astrophysics in Rome, and I will give this presentation also with the help of some of the ASAP participants, especially for the last part of my presentation. So indeed, I will talk about these 2 points that are in the title, so very simple overview, future perspective of space observation and importance of artificial intelligence and machine learning advancement. And I will talk mainly about heliophysics, not generally about space observation, and in particular about in situ measurements. Now we will learn during the day a lot also of work on remote sensing and solar images, but I will talk specifically about in situ measurement. Not much, but a little bit. And then a disclaimer, this is not exhaustive, of course, and perhaps I forgot to cite someone, so apologize in advance. So first of all, heliophysics, what are we talking about? Heliophysics combine the science of the sun, corona, heliosphere, geospace, magnetosphere, ionosphere, thermosphere, mesosphere, and upper atmosphere of the Earth and other planets. So here I give a list of processes we are interested in because it is important since we are now facing the need of making a step forward in the way we are doing our observation. The process we would like to understand, which are part of the heliophysics and are also important for the space weather, as that has been talked about, which Enrico just made this presentation, are mechanisms of energy mass and transfer and release during phase and coronal mass ejection, heating of solar wind plasma, solar wind streams, and other structure, solar energetic particle acceleration. Then we have the process of the mass energy transfer from the solar wind into the magnetosphere. When the solar wind arrives at the Earth orbit, we have several magnetospheric processes. Magnetosphere is very dynamic, so it is a very complex system. And then we have coupling of magnetosphere and ionosphere, galactic cosmic rail, and then we have also solar and magnetospheric plasma interaction with different planetary environments in our solar system. So we have a number of underneath the universal process that are involved in the phenomena that I've just described. And we didn't understand this process, despite the fact that they are fundamental process. And one of the reasons is the one that also Enrico mentioned, is that different scales are affected by different physical processes, and the interplay of this process results in complexity of this plasma, of this phenomena. And then also this determines their large-scale effect. So we start with the very, very, very small scales in which particle and electromagnetic fields are involved to very, very large scale effect. So to ultimately understand this, what we need is multi-spacecraft observation at all scale, possibly, electron, ion, and fluid and system scale, and then also remote sensing for advantage points. So there has been a lot of different missions in the past. This is actually an old picture regarding the NASA Heliophysics System Observatory, an old mission because some of these missions are targets are identified as in formulation, but indeed have been launched. For example, IMAP. Here we have Solar Orbiter that is giving a lot of result, and some other mission. But you can see already from here that we have many missions. And this, I mean, we go back in time to the 70s. Oh, no, this is not interesting for us. Okay. See, okay. And then we also have ESA mission. This is just to give, I mean, we all knew about all these missions, but at some point it's useful to recall which is our past, the many missions we had, and which is our future. And because this is an impact on what we want to like to do when dealing with all the data that came and will come from all these space missions. And then these are past, and nowadays mission is a mixture in some way. And this is all the ESA mission that have been done in the past and what are the mission in implementation. So there are a lot of mission regarding planetary and other kind of. There is one mission that is regarding the magnetospheric dynamics, that is MILE, and other mission also astrophysical mission. But we will concentrate more in the our heliophysics mission. So this has been the past. For the future, we have some mission. And here I would like to recall what once again Enrico said. We are at a plateau of our let's say progress in space physics. One of the reasons is that we are lacking new observation, new particular observation. And indeed, we are going toward an era where we are really aiming for multi-point observation and multi-scale observation. So, for example, this is a proposition for an ESA M7 mission. It is a candidate in a competitive phase A and targets two ESA Voyager 2015 teams, which are magnetospheric system and plasma cross-scale coupling. And this mission indeed is based on the use of multi-point measurement. In particular, for this mission, it is foreseen to have 7 identical small sat that are called sister spacecraft, which flow in a constellation that is the information in a tetrahedral formation sharing one coordinate. So the point to focus here is the multi-point characteristic of this mission. And this is a very crowded table, but here is the payload of this mission. And this payload is more or less, sometimes it is simpler, sometimes complex, but this is the kind of payload that is in a plasma. It is embarked in a plasma mission. So this is important because we have to do with a lot of measurements, and this means a lot of data. So, for example, we have 3 instruments for the measurement of the particle distribution function, for ion and electron at high scale, for mass-resolved ion distribution, and for energetic ion and electron distribution. Then we have a set of measurement of payload that has the goal to measure electromagnetic field, the DC and the variation of these fields. So this is just to share with you, probably all of you have already awareness of this, that we have to do with a lot of data for this kind of measurements, and we have to do with a lot of data that we have to download at some point. So this is important for the second part of my talk, because in this case we do need a lot of telemetry, and we do need some means to facilitate the downloading of all this data. The other mission that foresee a multi-point constellation is Helios Worm. It is a NASA mission. This is concentrated on the study of turbulence in the solar wind, and it comprises 8 microsatellites and 1 mothercraft. And again, these satellites are equipped with several instruments that are used to characterize the plasma that is observed during the orbit. And here again, you can see that this is an orbit that goes very far from the Earth. And again, in this case, we have to be able to download a lot of data and to download them for far away from the Earth. So these are 2 typical missions, very important missions that are in. This is practically has been accepted. The Plasma Observatory is under selection, will be the selection between the 3 competitive phase A mission will be in June. But I mean, there is indeed a need for this multi-spacecraft measurement. And here is the programmatic framework. And it is, there is an international scientific community that has identified the strong need for this new era for space physics. This is connected again what mentioned before, because we have arrived at a point that we have a lot of data that we need to analyze, and also we need methods to analyze them. But we also need a leap forward in terms of observation, because the magnetosphere is a system of systems where interconnection are fundamental, and so the current flint cannot answer the scientific question due to a lot of reasons, and everything is making process. For example, simulation. We saw a lot of simulation that are indeed very good. And so now what we need is indeed this kind of constellation. It is not only Plasma Observatory or Helios Worm. As I said, there is, the need from the community to have also multi-point observation in the magnetosphere. So we are talking about, for example, the LINX magnetospheric constellation that foresee 24 spacecraft that is focused on mesoscales. So this is more or less in terms of heliophysics, particularly the magnetospheric physics, the situation. And the message that I want to convey to you is that indeed we are making progress with artificial and machine learning, with theoretical interpretation, with simulation. We will have opportunity to make progress with the kind of observation that we are doing, and we have to put all these things together, indeed, for a new era. And it is an international effort, of course. Then we have another, phenomena that I would like to cite here. We have the CubeSat exploitation. So these I takes from this nanosat.au database. You can see here how the CubeSat use and nanosat use has enhanced in the last, 20 years. Also, ESA, for example, has been developing CubeSat, and here there is these new things because we do have CubeSat that go beyond the LEO orbit. And these are mainly by university, institute, and space agency. So CubeSat are indeed evolved a lot in these last periods. And CubeSat could, at some points, be so numerous that we do indeed need, for example, to further develop automatics use of program on board for many, many reasons. For example, in the CubeSat, this is really used, for example, for automatic determination of the orbits or automatic detection of other CubeSat so that it is very it is facilitate to avoid, for example, indeed collisions, as we are mentioning, but they are also used for science and for space weather. Before going to the description of what has been done, of what we have been doing in ASAP to address some of the challenges that are that we face with this new evolution of space mission, I would like only to show one slide regarding this mission that is called Heliospheric Pioneer for Solar and Interplanetary Threats Defense. This is indeed a mission that is being developed in a program that is ESA GSTP program. This mission is a pathfinder. It will eventually, if everything goes well, orbit in a never explored orbit that is such that this CubeSat will stay for a long time, moving very slowly along the Sun-Earth conjunction, but much more far away than L1. And so this would permit indeed a forecast that is much better than the 1 hour forecast that we do have at L1. And so there is the payload on board. We have a radiation monitor, a solar wind analyzer, and a magnetometer. And indeed, the idea is to put some algorithm on board that are able to make some onboard prediction of some space weather phenomena so that it is possible to have a prediction and a forecast horizon much better than it is now. So I would like, after this very non-exhaustive and panoramic of what is ongoing in terms of space mission for the heliophysics and space weather disciplines, I would like to go to the actual work that we have been doing within ASAP. So one very obvious observation, okay, we have many missions. Of course, not all these missions have been operating simultaneously, but the idea is that indeed we have a lot of missions and we have limited infrastructure at the Earth to receive all this data. So we have to, every time one designs a new mission, has to face the fact that he has to demonstrate that he's able to download enough data to reach his scientific objective. And so in this sense, it is indeed very valuable to focus on some goals and to work to reach these goals. So, for example, again, enhance the capabilities of autonomous triggering of special measurements modes on board. So indeed, this would help a lot when defining the operation of a spacecraft, improve the capability of selective downlink of plasma environment parameters. So we have indeed telemetry constraints and also onboard memory mass as constraints. So you have to always to make a trade-off and try to get on Earth, I mean, the information that is more important for your scientific objective. Then we have this goal of develop onboard data analysis of three-dimensional particle distribution function, again, to maximize the particle measurement exploitation, enhance the capability, for example, for solar image analysis. This we did during these 2 years of ASAP process. And the other things is indeed optimizing timely onboard prediction capability of solar energetic particle hazard. So indeed, we focused on this, bunch of goals, and indeed some work has been done during these 2 years. Here I simply summarize some of the developed or optimized algorithms that have been studied. I will say some word about some of them. I don't know how much I have. Okay.
Yes. Maybe 4 or 5 minutes.
Sorry. It's very. It's not it's not much. But again, this is okay. Bus triggering and selective downlink algorithms. We have these on board. We have a couple. No, we have analyzed a few. Different ones, some are more promising, some less. Then we have different board analysis of particle distribution function, image analysis. We will learn later on a lot about this. And then we have this set prediction algorithm. So this is the bus triggering and selective downlink. What, in a few words, this permit is to permit this kind of, here I mentioned one of these, but this kind of algorithm predict to permit to identify the magnetospheric regions. So this can be used to trigger particular modes of operation on board, or to decide which data, which particle interval in time we want to download. Onboard data analysis of particle distribution function. Particle distribution function can be indeed non-Maxwellian. And so non-Maxwellian and with a lot of population at the same time. So downloading the particle distribution function, it's not easy because there are a lot of information. Especially if the resolution in the phase space is high, and if we want, especially if we want them at a very high time resolution, as we need, for example, for studying kinetic physics. So in this case, it has been used the Gaussian mixture model to try to separate the proton and alpha population on board when with instrument plasma analyzer that do not have the capability to distinguish the mass of the ions. And so this is indeed possible with this unsupervised clustering with this clustering that is a form of unsupervised learning. And what is possible to do is indeed starting from a distribution function that does not distinguish, in which are not distinguished protons from alpha, to identify the two population and reconstruct the distribution function both for alpha and for protons. Then I would like to show you another example of using these Gaussian mixture models. In this case, we can use this kind of algorithm to understand to give an estimate of the complexity of the distribution function. If this distribution function is composed by multiple population or other feature, we can understand this using identifying this different population and giving a criteria for understanding the complexity. And this can be used indeed again to identify regions that are interesting for the kind of phenomena that are going on. In this case, for example, there is a reconnection event going on, and we can see here that with this Bayesian information criteria, big parameter, we can easily identify that these periods for us is very interesting. And so we could use it for example, selective downlink. Then we have this variation autoencoder. This is a very interesting work. This is a probabilistic encoder-decoder architecture that is designed to process solar images from, in particular, the Solar Dynamics Observatory. And this permits us indeed to detection anomalies in active region. And this indeed can, for example, help us in early detect space weather phenomena, but also to help us in selective downlink once again. But also, and this is, this use of this algorithm has always these three components, no? Can be used operational, but can be used also to infer physics that is underlying. We learn a lot about this from the Enrico presentation. So this is indeed described very well here. I will not go into the detail because I think I'm running out of time. The last algorithm that I would like to present is this indeed expert algorithm for the solar energetic particle prediction. So we have some inputs here, fair location, and then integrated flux of solar X-ray, and then also other inputs. The technique is a logistic regression and evaluate the probability of solar proton energetic events occurrence, basing of indeed the input parameters that I just mentioned. And this is the output of the algorithm. This can be used indeed on board, and we, for ASAP, we optimize the algorithm so that this can be used in different locations in the heliosphere, and this could be particularly useful thinking about human exploration, for example. So my conclusion here are that we have a large amount of observation available, and so we need new tools for understanding. We need a step forward in modeling a new data analysis method and interpretation. But for the future, we already know that dune observation will be necessary. And so we need to enhance our capability to exploit this in situ space, for example, multi-point observation and also remote sensing with onboard application. And this is my last slide.
Thank you, Federica, for a very interesting review of all the things that are happening in ASAP. What are the questions in the room?
So we are waiting for the future.
Also, questions in the chat. We will be welcoming those questions. Yeah, okay, I have a very basic question. So what scales will you be able to study with Plasma Observatory?
Ion and fluid.
Ion and fluid scales, yes.
As you know, this M7 mission has a cost cap. And so one of the constraints is that you have to be in the cost cap, and having a constellation, for example, as was the constellation of Cross Scale, which was the very first, multi-scale missions that was proposed, is indeed above the cost of this class of mission, because you have to have, more than 7 spacecraft. So.
Okay, thanks.